Have you ever noticed how your phone predicts what you're going to type next? Or how Spotify recommends songs based on what you've been listening to? This magic happens because of sequential data. But what exactly is sequential data and how do we predict it? Sequential data is information where order matters. The meaning of the data changes based on the sequence in which it appears. Let's look at a few examples. Sentences. The order of words in a sentence determines its meaning. For example, I am happy is very different from am I happy? Medical signals, like an ECG, where the sequence of electrical signals reveals the heart's condition. Video clips. Each frame depends on the ones before it to tell a meaningful story. So, when we deal with sequential data, we're working with patterns that unfold over time. A common task here is prediction, like guessing what comes next in a sequence. Let's take an example to understand how we predict sequential data. Imagine you're given this sentence. The President of USA in 2020 was blank. The goal is to predict the next word. The correct answer here is Trump. Now, how do we go about making this prediction? There are a few common methods, and each has its own strengths and weaknesses. The first approach is the fixed window method. In this method, we only look at a fixed number of words before the word we want to predict. For example, if our fixed window size is 4, we consider USA in 2020 was to predict Trump. This works well for short-term patterns, but here's the problem. Fixed windows can't handle long-term dependencies. For instance, what if the important context appeared earlier in the sentence, or even in a previous sentence? The fixed window method won't see that context and might make the wrong prediction. The next method is treating the entire sentence as a bag of words. Here, we ignore the order of the words and just count how often each word appears. For example, the sentence, "The President of USA in 2020 was," might look like this, where each position corresponds to a specific word and the value shows how many times it appears in the sentence. But this method has a major issue. The bag of words model completely ignores the order of words. Let's look at these two sentences. The food was good, not bad at all. The food was bad, not good at all. Both sentences might look identical as a bag of words because they contain the same words, but the order of the words changes their meanings completely. To solve these issues, we can use a bigger fixed window to capture more of the sequence at once. For example, if the sentence is, "The President of USA in 2020 was Trump," we can use a larger window and represent the sequence in a one-hot encoded format. Each word is converted into a vector, where 1 means the word is present at a specific position. 0 means it's absent. For example, this sentence might look like this. The bigger window allows the model to consider more words at a time. But even this approach has its own challenges. There's no parameter sharing. What does that mean? Let's say the model learns something about the word president at one position. It won't apply this knowledge if president appears at a different position in another sentence. This makes the model inefficient because it has to relearn parameters for the same words appearing in different positions. So, predicting sequential data isn't as straightforward as it seems. Fixed windows, bag of words, and bigger windows all have their limitations. To truly understand sequences, we need smarter models that can capture long-term dependencies and preserve the order of information. In the next scenes, we'll dive into advanced solutions like recurrent neural networks, RNNs. If you found this explanation helpful, give this video a thumbs up and subscribe to SmartSlides for more exciting contents. See you next time.